Okay, hello everyone. Welcome back to lecture 7 of Introduction to Stable Homotopy Theory. I realized after thinking about last week's lecture that some of you might actually not know what a filter colimit is, since I'm not sure if it was introduced in some of the previous classes. So I decided to give, since we're going to need to use them today, I decided to give a very short primer, not much, but just a quick mention about filter colimits and how they behave. So I hope it's not going to be too boring for those of you that already know what they are. So, okay, let me start. So let's say that S simplicial set is filtered if for every kappa finite simplicial set, by which I mean finitely many non-degenerate simplices, and every map K to S, we can extend it to the cone. Okay, that's a general definition, but we are actually going to be more interested in this example. I'm going to give us an exercise. So if P is a poset, the nerve of P is filtered, and I'm putting the nerve between parentheses because, as I said, I'm going often to omit the nerve. If for every P prime in P, there exists a Q that's greater than both of them. So that's actually the intuition you should have. In particular, as an example, and in fact, it's pretty much the main example we're going to use, and the natural number with the standard order and the integers, the standard order are filtered.
Could you give an example of a filtered simplicial set which is not of the form nerve of some poset with this condition?
I could. It's not going to be super interesting, I'm afraid. Let's see. So, in a sense, that's essentially the only example. You can reduce every filter colimit as a colimit of such a poset. But let's see. I mean, the classical example actually is that if C is an infinity category with all finite colimits. So for example, take, I don't know, C, the nerve, again, the nerve, I'm going to parenthesize it because of finite sets, then C is filtered. That's the other example that sometimes show up, although I don't think we're ever going to use it.
Okay, thanks.
You can actually give more exotic example if you want, but I don't remember them off the top of my head and they're not that important. And a filter colimit is just a colimit parameterized by such a filtered simplicial set. So, okay, and then I'm going to give you 3 properties. Okay. So one is that the forgetful functor space star to space preserves filter colimits. This is not true for all colimits. For example, the co-products, as you know, are given by the wedge in pointed spaces and the disjoint union in spaces, so they're not preserved. The wedge is not the co-product in spaces, but it is true for filter colimits. The second one, which is actually the most important, is that filter colimits in space, and therefore also in pointed spaces, commute with pullbacks and finite products. And since people asked me for a reference, I found one. It's actually not like a reference you might want to consult probably, but it is a reference nonetheless. I'm trying to think if I can think of a better proof of this fact, but at least I'm giving you a reference. It's in Higher Topos Theory 5333. Essentially, the point is that weak equivalences in simplicial sets commute with filter colimits, and so you can reduce to a problem in simplicial sets where you do it by hand. And there is a small detail because you want to compute homotopy pullbacks and not pullbacks, but as you know, homotopy pullbacks can sort of be computed by hand. And the third is, well, it's actually more than a property, is actually something that's a consequence of all the things that of 1 and 2. So we have pi note from space to set commutes with all colimits because it's the left adjoint to the inclusion set into spaces, and that's very easy to verify. Actually, I never remarked it before in this class, but it's very easy to verify, and you know that left adjoints commute with all colimits, and therefore, using 1 and 2, pi n from space star to set, which can be thought of the composite of this map omega n to space star to set, to space to set, this is the forgetful phantom, commutes with filter colimits. That's because omega is a pullback, and by property 2, filter colimits commute with pullbacks. So I can put actually, here is property 2, here is property 1, and here, and this pi note is the observation. And this is all I wanted to say actually about filter colimits. And I wouldn't say, property 1 is actually kind of easy to do by hand. It's not a very deep statement. You have to think about how colimits are computed in space star. Property 2 is a non-trivial statement. That's why I'm giving a reference. And property 3 is basically an observation at this point.
Question. So do I calculate the filter colimit in spaces simply as the filter colimit of topological spaces? Like
yes and no. Depends exactly of your diagram, but mostly say yes. Let me say yes, mostly.
Okay.
I'm sure it's true in simplicial sets.
Uh-huh.
spaces, there are always these issues about stuff is cofibrant enough, they're well pointed, and all these sort of things that I'm.
But aren't all spaces cofibrant?
No. Oh, spaces, yes. Pointed spaces, not. So, okay. The answer is probably yes, but I don't want to commit strongly to it.
Okay.
Because I might get confused. Okay. And again, if you need an example of filter colimit, actually, we will use mostly this poset here. This. Okay, are there questions about this?
Excuse me, are colimits in pointed spaces then kind of like built like in the topological one category setting?
No, not really. They're kind of, okay, in the case of N, which is the case we care about, colimits here, colimits indexed by N can be represented by the mapping telescope. In top. So for example, let me give it exactly. So suppose we have this functor x from N to top, which concretely means you have x0 goes to x1, goes to x2, goes to blah, blah, blah. The colimit where x can be represented as the disjoint union of xi times the interval 0, 1, 0, sorry. Well, it doesn't really matter. Modulo the relation that you identify. So if this is f0, this is f1, this is f2. If I fix1 0, sorry, no, I want to say x1 is identified with fix0. So I'm sometimes you see this drawing like this. Where these are the mapping cones, sort of. And very often it is computed as the colimit in spaces.
No, I think I meant,
sorry.
Yeah.
Cylinder, sorry. It's mapping cylinder, of course.
I meant the fact that when going from normal spaces to pointed spaces, you compute co-limits by adding a terminal object to the
no, not quite. What happens, so if you have X a map from I to spaces, to pointed spaces, you can take it in spaces. So let me give a name, I can call U this for the sake of things. And you can compute the colimit of X by taking the colimit of UX. And here you have a colimit of the point here, since X UX receives a natural map from the point, which is given by the pointing, I mean the constant functor at the point, and then you collapse this. So for example, if you look at what happens for the mapping cone, you take the mapping cone in spaces, but then you have to collapse this constant colimit of the point. So you take, if you want, what we can write is that the colimit of X is the colimit of X, when I forget the pointing, modulo the colimit of the base points. And what happens is that for filter colimits, this guy is already contractible. So I'm not doing anything.
Okay, that's what I meant. Thank you.
Okay, good. Let me write it. Already contractible if I filtered. This is actually more general. This is true for all shifted colimits, for example, but I hope I'm not going to use it. We'll see. Okay. Okay, that's what I meant when I said that this property 1 is more of a remark. You have to check that colimits in pointed spaces are actually given by the formula I just gave you, but then after that, it's kind of easy. Property 2 is actually non-trivial. So property 2 does require some non-trivial amount of work. And I haven't found a very short argument for it, unfortunately. But when I state the descent statement, you'll see that this follows from the descent statement, for example. And I think I'm going to take the descent statement as a black box and derive all properties of colimits in spaces from it in the end. Because I think that's the most honest approach one can give. Okay. Are there other questions? Let me wait 1 second. I've been told I'm writing too fast, so sorry for that. I'm trying to wait. Okay. After this parenthesis, I say we go back to spectra. And let me recall what we did last time. And then today I'm actually going to talk about filter colimits of spectra. So that's why this parenthesis was perhaps needed. So, okay. So last time, so recall, we have spectra. This is as objects, these sequences. And maps, oh, sorry, I call them E. And I probably should stick with E. And map from EF and spectra, the limit, map E0, F0, omega, map E1, F1, omega, etc. And we saw that there is a functor, omega infinity, from spectra to pointed spaces. That sends E to omega infinity of E, which is by definition E0. And the map on mapping spaces is just a projection on the first component of this limit. And it has a left adjoint. Sigma infinity from pointed spaces to spectra, which sends X in this sigma infinity X, which is this functor Q sigma n X, n greater or equal than 0, and then the obvious delta n Q sigma n omega Q sigma n plus 1 X, where Q from pointed spaces to pointed spaces is this thing, Qx is the colimit over n of omega n sigma n. This space whose homotopy groups are the stable homotopy groups of X. I record here, Pi of Qx the stable homotopy groups of X. And we saw last thing we saw is that maps spectra from sigma infinity X into E is the same thing as maps in pointed spaces from X to omega infinity of E. I'm not going to repeat the proof. It's essentially writing a big diagram, and once you write the right diagram, the proof falls down almost by magic. And the diagram, you can find it in the notes or in the video of last time. Okay, we good so far? Okay, good, because now I want to think of, I want to say something about limits and filter colimits in spectra. And then I'll use that to actually say something about push out in spectra and give presentations of spectra. Okay, so, okay, let me do first this proposition. So suppose E from I into spectra is any diagram. Lim I E exists, and it's given by the spectrum, which is lim I En I, or maybe I should say EIN. Sure. EIN plus 1. This is actually kind of easy. The first observation is that this fact that I wrote is actually a spectrum. That is that this delta n is indeed an equivalence. So if you want, their compute limits in spectra are computed level-wise. So why? So first, we need to check that delta n is an equivalence, but this follows because omega commutes with limits. That's because limits commute with limits. So you have like omega lim I EI plus 1. Well, you can bring it this inside. In fact, you get a canonical map exactly in this direction, and you get lim I omega E plus 1, and then you can take the delta n I, and you get equivalence. And that's our delta n limit. And then now we just need to check that this map from any spectrum to this lim, let me call this lim IE, because that's what it is. That's the limit over n in pointed spaces from Sn to lim I ENI, sorry, EIN. And then we just move the limit out as you're allowed to do. and exchange them. And then you get just spectra F to EI as we are required to check. Again, this is not a hard proof, but I am secretly using that limits commute with limits here, or generally that omega commutes with limits. So, okay, so in particular, spectra as whole limits. Other questions about this? Put it then. And then I'm going to claim that the same is true for filter colimits. The same is not true for colimits. We'll see a counterexample in, well, in half an hour, I think, where colimits are not computed level-wise. But it is true for filter colimits. And if you need an analogy for these, think of the case of abelian groups and sets. You have a forgetful functor from abelian groups to sets, and this commutes with all limits and with all filter colimits. But it does not commute with arbitrary colimits. Because, for example, the coproducts in abelian groups and in sets is very different. So that's sort of the same thing that's going on here. Not quite. There are some subtleties here in this picture, but it's a very good first approximation. So, okay, other propositions. So let E spectra be a diagram with I filtered. Then colline I E exists in spectra, and it's given by colline I E I n delta n. So colimits exist and are computed level-wise. And the proof, same as above, but it's very important, but we are using that omega commutes with filtered colimits. You can see, otherwise you cannot prove that delta n is an equivalence. Okay. But thankfully now we have, you can do the same proof. And now we have enough categorical nonsense about spectra to do some more work on them. I mean, this is still going to be rather categorical today, but it's going to be more interesting, I think. It's going to explain some of the key properties that make spectra work as well as it does. So I hope it's not going to be too dry. Other questions about this? No. Okay. Okay, so let me give a corollary. So loops of E is given by the spectrum E n minus 1 and Z delta n minus 1. So they're given by what's said as shifting. i.e. it's given by shifting. And that's just because we said that loops are computed, well, loops E is given by this thing. But this is given by the formula above. Because, you know, En minus 1 is exactly loops of En. And so, in particular, loops from spectra to spectra is an equivalence. With inverse. Ooh, sorry, no one corrected me, but of course the sign of the shift was wrong. Omega of En is En plus 1. No. Omega of En. No, omega of En is, no, I was right at first. Sorry. Sorry about that. Wait, how can that be possible? No. Oh, yeah. Yeah. Sorry. Everything is correct now. With inverse given by, sorry, but now this is given by this shifting. I'm sorry, this was given. Okay, I'm going to introduce a name for this inverse shift now.
Sorry, maybe I missed something, but how did you define omega E, if not like
omega E is defined as the pullback. I define omega in every infinity category as the pullback.
Ah, okay, yeah, okay, then.
Oh yeah, I probably should say also the zero spectrum is the terminal object. I didn't say that, but oh, I think I might have mentioned it last time actually. But okay, then it's the colimit over the empty set. It's the limit over the empty set. So this follows. No, sorry. Omega C, remember, is the pullback of this. As we saw that pullbacks are computed level-wise. Actually, put this somewhere else. Okay. And the point is, but we know that if omega has a left adjoint, this is given by the suspension, which is the push out along this other map. And so the suspension of E exists, and it's given by the above formula. Since it's an inverse, in particular an adjoint to omega. This is perhaps a small trickery, but it works. I'm actually not sure whether we're ever going to need to use this particular proof of the existence of the suspension. But since we're going to need to use that omega is an equivalence, I might as well notice that this implies that the suspension exists.
Sorry, maybe this question is stupid, but it seems to me that this is the reason why you have to take the co-limit of compactly generated infinity categories if you want to invert the adjoint.
Yes.
Yeah. Okay.
Well, presentable. It's enough to take the co-limit in presentable infinity categories. But okay, but I'm taking not the definition as a co-limit, but the definition as a limit. So
yeah. I just wanted that. If I was right with this suggestion.
Yes. In fact, it turns out that, well, okay, this is discussed in higher algebra somewhere in chapter 1. I don't remember the place. If you want to look it up more in detail. But okay. But even if you know nothing about compactly generated infinity categories, I hope this discussion, this existence of the suspension is clear. Okay, because now we're going to talk about presentations of spectra. Now that we have all, just a small amount of notation. Sometimes we'll write omega n of E as sigma minus n of E due to this remark above. So this is just a shifting operator. Now we're allowed to shift also in negative degree. That's just notation. Okay. So.
Excuse me?
Yes.
Just for the record, your argument here is that for the existence of sigma is that omega has an inverse equivalence, and this can be promoted to an adjoint equivalence, and then this must be sigma.
Yes, inverse equivalences can always be promoted to adjoint equivalences. That's just a formal trick. And we saw that if omega has a left adjoint, this has exactly the correct universal property for being sigma. That's we discussed a week ago, I think, or something.
Okay, thank you.
Yeah, sorry, maybe I don't know how familiar you are with category theory. This is just a general fact. If you have an inverse, that inverse is automatically both a left and a right adjoint. It's just playing with diagrams. And of course, you have to probably check that the classical proof in one category theory upgrades to proof in infinity category theory, but that's just the diagrams that you write are the same, so it's not. Once you're allowed to write diagrams, a lot of those proofs just go through verbatim. Okay, good. Now let me give a definition. So a pre-spectrum is a sequence En of pointed spaces and maps, you can call them Dn from sigma En to En plus 1. And the point is that I can use, now I have enough structure on spectra that for every pre-spectrum, I can associate a spectrum to it. To a pre-spectrum, we can associate a spectrum by taking the colimit and call it E, it's the colimit. So you start with sigma infinity of E0, but then you map to sigma inverse. So, oh, observation, this is the same thing as a map from En to omega En plus 1, but I'm not going to ask that this is an equivalence. It's just going to be a map. So this is sigma, let me write it like this. Omega sigma infinity E0. And this map is adjoint to sigma, sigma infinity is 0, which is sigma infinity of sigma is 0, because sigma infinity is a left adjoint and commutes with colimits, mapping to sigma infinity, E1. And these maps to omega square, sigma infinity E2, etc. And I take the colimit. And note that I did need both finite limit, both limits and filter colimits to be able to make this definition. And I'm going to think of these as a presentation of the spectrum E. So for example, example/exercise, if I take this pre-spectrum sigma n of x with maps from sigma n to, from sigma n to sigma n plus 1 of x given by the identity, the associated spectrum is what I called sigma infinity of x. And that's because you can see that this colimit, in fact, is going to be a constant colimit if you unwrap what it is. Using the fact that sigma infinity commutes with sigma, and that omega sigma is the identity, because omega and sigma are inverses. But I'll leave it to you as an exercise, perhaps. And we're going to see many spectra that are going to be given by this kind of presentation, but I want to, so if you think of spectra sort of as abelian groups, this is sort of like giving generators and relations for your abelian groups. That's how you should think of the presentation. And as you know, every abelian group has a canonical presentation where I take every element as a generator and just all the possible equations as relations. And I want to tell you that spectra have such a canonical presentation as well. So,
excuse me?
Yes.
Then this associate spectrum to a pre-spectrum is somewhat of a infinity left adjoint to the inclusion?
Yes, but I didn't define what maps of pre-spectra are because it's kind of fiddly and I'm not going to need it. So I can't make it precise right now for you because I haven't defined actually what maps between pre-spectra are, or mapping spaces between pre-spectra are. But yes, it is. There's going to be a spectrum. This is essentially a spectrification functor adjoint to the inclusion of spectra into pre-spectra, if you go define it.
Okay, so spectra is something like a locally presentable category, or
it is
monadic over pre-spectra?
Oh God, is it monadic? No, I don't think it's monadic actually, but it is a reflective subcategory of pre-spectra, if that's what you're asking.
Oh, okay, then I mixed up things. Okay, yeah.
I don't think it's monadic though. It's an omega accessible localization if that's what you want. But I don't think the inclusion proceeds with split shifted colimits. So I don't think it's monadic. But okay. But I might be wrong here. But anyway, this is sort of, you can think of this, I give you a bunch of generators and a bunch of relation given by these delta n's, and then this builds a spectrum. And by the way, historically, people work with what we're calling pre-spectra and call them spectra. And what we're calling spectra, they call them omega spectra. But then defining the maps is a bit fiddly, and I don't know, it's very much like working with groups by giving generators and relations and manipulating them. There is, as I mentioned last time, there is an amusing note by Nikolaus and Krause developing the theory of groups sort of by using only generators and relations and never explicitly writing down what a group is. And it is very similar to how the theory of spectra was historically developed. And I'm choosing a more modern approach now, and I think this terminology is what you're probably going to find out in more recent papers. And I think it's simpler in the end. But, okay, so lemma, standard presentation. So let E be a spectrum. Then the natural map colimit for n omega n sigma infinity En, where En is the n space of my spectrum, to E given by the maps sigma infinity En sigma n E adjoint to this last equivalence is literally the identity actually for how I define things. E is an equivalence. So as we were noticing, a spectrum does give me a pre-spectrum, and I'm telling you that, yeah, the associated spectrum is indeed the same as the original spectrum. So this is like taking all possible elements of my group as generators and putting all possible equations as relations. Okay. Okay. Questions about this statement? Let's see the proof. And the proof is just going to see what these maps are from this colimit on n sigma infinity En into F. And well, that's the limit over n maps omega n sigma infinity En F. That's just moving the colimit out. But then I'm using that omega and sigma are inverse equivalences. And I can move the omega on the other side as from sigma. And then, so sorry, this is maps in spectra. Because now we can move to maps in pointed spaces. Infinity sigma and f. That's here because of the adjunction sigma infinity omega infinity. But then this is canonically, since sigma n is the shift and omega infinity takes just a zero space, this is just maps em to fm. And this, oh, sorry, no limit anymore. And this is, well, actually it's the definition of maps in spectra from E to F. And that's true for every F. So when a map induces an equivalence of mapping spaces for every F, then it is an equivalence. This is just, if you want, this is just a tautological statement, but it's good to have it written down. Okay. Okay, and now that we have the standard representation, actually we can prove that spectra has actually all colimits, not only filtered ones. So far we have only used filtered colimits, but in fact spectra has all colimits, thankfully, as it should. And as a corollary of the standard representation, spectra has all colimits. I see desperate faces here. Do you want to ask something? Okay. So as a proof, so that we have a functor from I to spectra. And well, okay. We can take this colimit, we can take a colimit EIN, and these maps from delta n from colim I EIN to omega. Oh, okay, I guess I'm writing of them. And this is not a spectrum anymore. It is just a pre-spectrum. But we can consider the spectrum presented by it. So this I'm going to call it colim IE because that's what it's going to be. It's going to be the colimit over n of omega n as sigma infinity colim I EIN. And now you just need to show that it does satisfy indeed the universal property of the colimit. And that's again going a little bit faster than before because it's the same proof. Oh, sorry. and again by commuting limits. Oh, that's mapping space. Now, this is not useful at all to compute colimits. I mean, even if I gave you a formula for it, but it turns out to be terrible to use, but at least we know that they exist. They're there, and I'm going to be able to get better formulas now that I can manipulate with them, confident in their existence. And sorry, this proof maybe I went a little bit faster, but it's the same trick as before. Okay. Maybe the homotopy prospector, I'll do it later. Yeah, I'll do it later. Now I want to give you what is the single most important property of the category spectra. It's in some sense, the category spectra can be realized as starting from pointed spaces and imposing this property I'm going to prove now. And that's going to make everything work. So let me, so let's pay attention. So proposition, let us consider a diagram, consider a square in SPA, we call it x0 goes to x1, x2, x1, 2. Then let me give it a name actually. Star is a push out square if and only if star is a pullback square. And this property has an important name. This goes under the name stability. And if you notice that the name of this class is Introduction to Stable Homotopy Theory, that's not a coincidence. That's this property that makes stable phenomena actually happen. And we already saw a special case of these when I showed that the suspension was the inverse of the pullback. We're going to prove the general statement now. And if you remember from last semester, we discussed the Blaker's-Massey theorem that said that in spaces under sufficiently high connectivity assumptions, something like this was true, but it was a lot weaker. This is just true on the nose. A square is a pullback if and only if it's a push out. And that's kind of magic. And actually, let me deduce a corollary before I prove this. Let EF2 spectra, then the natural map from the disjoint union, from the co-product, sorry, I shouldn't call it disjoint union, to the product. This is because it's a pointed category. This corresponds to the matrix 0, 1, 1, 1, 1, 0, 0. Is an equivalence. This sometimes called, because under the name of SPA is semi-additive. A co-product and the product are the same. We will write E direct sum F for the common value. This is something that happens also in abelian groups, for example. Co-products and products are the same via this canonical map. And this is an example, for example, of colimits that are not computed pointwise. Because pointwise will be taken like En wedge Fn, but this is not going to be a spectrum. You can actually prove this directly if you have a lot of patience, but I'm just going to get it as a consequence of stability. So proof. Let us consider the squares. Which one do I want? I want this one. Okay, these are very stupid squares, but these are push-out squares. Because parallel arrows are equivalencies, well, they're the identity, so not much is good. So their coproduct is a push-out square. Oh, am I doing the wrong direction? No, sorry, these are pullback squares. And so their product, I'm doing the wrong direction. The product is a pullback square. So here we have 0 goes to E goes to F. To E times F, and that's a pullback square. Because products of pullback squares are pullback squares. If you want products commute with pullbacks, that's just a statement about limits commuting with limits that we've used several times. Yes. But by stability, it is a push-out square. And well, that's actually the thesis. Because what is a push out along the initial object is just a coproduct. Push out E. This seems magic, and it sort of is. You try to do this proof in other places, it doesn't work, but the magic of stability just makes it true. And in fact, stability is what will make colimit in spectra actually computable. Well, the row formula I gave you earlier is not. But I'm going to need the existence of colimits to prove stability. So that's why I gave that formula. So, okay. Proof of stability. So, okay, we have our square. Let me show one direction. Okay, let me suppose we have it's a push-out square. And show push-out implies pullback. And the other is exactly the same with the diagram written in the opposite direction. So okay, we enlarge this diagram. So we first add maps to 0. Okay, so far so good. And then we take the push-outs here. And that's fine. And then we take further the push out. I'm going to ask you, what is this push out? Well, if you take the push out here, also this big square here is going to be a push out. So this guy has a name, then this name is going to be sigma x0. Okay, let's play this trick again. Let's add this and let's take the push outs here. Okay, what are the push out here? Well, okay, for example, here, this is the same thing as taking the push out of this big square. So this guy is called sigma x2. And same way, this guy is sigma x1 by considering this square here. And again, let's get crazy and take further push outs, and that's sigma x1, 2. Okay, we have this diagram. It's a nice diagram. Now, let's see if I can do the proof as I have it in my notes, because I'm going to look at parts of this diagram and take the limits of these parts of the diagram and see what happens. So let me select some pieces of the diagram. So there's this, there's this, yeah, and then there's the well, this one. Notice that we also have arrows like this because 0 is the initial object. So I have these arrows here. That's just not doing much, but I'm going to need it for the third piece of the diagram. Take an orange. And that's the trickier one, perhaps. It's this sub-diagram here. And I get, maybe you cannot see the yellow one though. So actually, let me change the yellow color to this purplish one. So, okay, that's perhaps the moment where I should confess that I'm colorblind. So I have literally no clue of which colors I'm using right now. So if I call something red and it's green or blue and it's purple, tell me, but I cannot help much with that, unfortunately. I have an app on the phone that tells me which colors are what, but it's a bit inconvenient to use now. Okay, and I guess, yeah, let me actually select this. And orange. There's also this, I guess this portion of the diagram here. It's a very stupid sub-diagram, but I might as well select it. And notice that each of these sub-diagrams actually map to the next one. They lie, this is a big poset, and each of these is just above this sub-poset. So I actually get maps from each of these sub-diagrams to the limit of these other sub-diagrams. So, okay, what are these? Let me write it here. So I have x0, that's the limit of this silly one object sub-diagram. And these maps to the limit of that thing, which is exactly the pullback that we want to be the same as x0. So our goal is to prove that this map is an equivalence. Okay, then you can take that other sub-diagram there, the reddish one, I'm not sure. And that's just omega sigma x0. Because remember, omega is the pullback of this thing. This map, maybe let me move it. I need a little more space. And then the trick part is what is the pullback of this other diagram, the limit of this other diagram. So let me tell you the answer, and then I'll try to justify it. is just the pullback of omega sigma x1, omega sigma x1 to omega sigma x2. Okay, granting that, I'm going to justify it in a minute, but granting that, you'll notice that this map is an equivalence because omega and sigma are inverses, and this is just the co-unit of the adjunction, the unit of the adjunction. And the same is true for this. This is an equivalence. And then by just applying the 2 out of 3 arguments repeatedly, everything is an equivalence in this diagram. Because, for example, this guy, this arrow here, has both a left and a right inverse. So it's an equivalence. But then all the arrows in the diagram are equivalences. It's kind of a magic argument. It's due, I think, to Charles's rest, this particular simplification of the proof of stability. I'm not exactly sure where he took it out of the head, but it's a cute proof. You can actually give a slightly more conceptual one by writing bigger diagrams, but it's not really worth in this particular context. It's more useful when you do equivariant homotopy theory. Okay, so let me actually, I have to convince you of the limit of this diagram here. So let me copy it. Actually, let me leave it here for you 1 second. Let me leave it this for you 1 second. But okay, is this clear so far? Yeah? Okay, so let me actually compute this limit. And where we have this thing here. And the trick is going to compute the limits, one piece of the diagram at each time. So this diagram, you can see 3 diagrams here that I guess I'm going, since I'm going through these colors, you can picture them, for example, like this, and I guess like this. And the idea is I can compute this diagram as the diagram, the limit of this bigger diagram. Yeah. Maybe this 0 is too high. Well, this is just so the limits of this bigger diagram is exactly the limit I complained about. The limit I claimed, because you can just first compute the limits in this. Like this, and let's see, like this, and like, which color do we choose? This one. This. And this gives me a map of diagrams like this. And this is in fact co-initial, which means that they induce an equivalence on the limit. Because I'm just multiplying the amount of zeros and it's not doing much else. I'm just sending all the rows of zeros to the same element and not doing anything else. Okay. I don't know if you can see the geometric picture on these diagrams, but it's just collapsing the zeros. So you don't, you get the same limit. Okay, so that's the proof of stability. Somehow magic fashion. And okay.
Was it really the entire proof? Don't we need another direction also?
Oh yeah, you need the other direction from pullback to push outs, but you just write the same diagrams with the arrows in the opposite direction, and this, there is some kind of symmetry here. And there you have to use that sigma omega x goes to x is an equivalence, which is also true. Yeah, you're right. You need to, people always write down only one of these directions because the other is literally flip all the diagrams, and you get the same proof.
I have maybe two questions to stability. Is there any reason why one should expect this statement? And the other one maybe is there one category with this property?
No. So the answer to your second question is no. In fact, let me put it as an exercise. That the exercise is going to be quite easy, actually. A one category is stable if and only if it is the zero category. And actually by stable, I mean it has finite limits and colimits, and the push outs are the same thing. It's pointed and push outs and pullback. So yeah, in a sense, the answer to the question is actually yes, there is a one category with this property, but it's not a very interesting one category. In fact, that's actually a good exercise if you want to try to prove it. The trick is to use the fact that omega is an equivalence to show that the Helm sets are the same thing as their loop space, and or if you want the omega as a functor from sets to sets is just a constant functor at the point, from points and sets to points and sets. So you can actually prove. So okay, and why do you expect this property? Well, let me put another exercise, which might or might not be enlightening depending on your background, but use stability to deduce that the homotopy category of spectra is triangulated. If you've seen triangulated categories before. So that's maybe it's not be very helpful, but people that were thinking about these things had seen triangulated categories before and they thought they were useful. And in fact, stable categories are sort of the modern, better version of triangulated categories. You can give a much shorter definition. It's generally easier to prove that something is stable than to give the triangulated structure. In a sense, stable categories, so let me list it as a slogan, stable categories, well, infinity categories actually, really, is where you do homological algebra. As a slogan, is the correct environment with the right properties for doing homological algebra. So, is there a reason? Well, yes and no. I also want to say that it's not true that every triangulated category arises from a stable category. There are some counterexamples, but they're somehow pathological, and you're not unhappy that those are excluded. There is an example due to Schwede. I don't remember, it's kind of weird. So I don't remember the details now, but it's like take two torsion abelian groups and you equip it with a crazy triangulated structure. Oh, and it's triangulated, sorry, and I should say that the suspension, that the shift is given by suspension in this triangulated structure, if you've seen a triangulated structure. And exact triangles are exactly exact sequences and exact triangles are things coming from push out, pull back squares like this. But okay, but actually let me give you a slightly remark that might make you this stability property look more natural actually. So let A be an abelian category. So for example, abelian groups, or I don't know, R modules, and I don't know, sheaves of such, etc. Pick your favorite abelian category. Then a square x0, x1, x2, x1, 2, where this is monomorphism, this is epimorphism, is pull back if and only if it is push out. So you have a weaker form of stability. You have to put some restrictions on these squares that you have. But also this also might give you some intuition in this property. This is exactly the property in abelian categories that if you take the kernel of the co-kernel, you get back the image. This is, let me write it. Co-ker is co-ker of ker, which is the first isomorphism property for abelian groups, I think. If I recall my first year class, it's been a while ago, but. So you can think of this as sort of a weaker version of stabilities, but when you work with infinity categories, you actually can have like fully stable things. And that's so much better. That gives you so much more flexibility. Okay, I was thinking of defining the homotopy groups of a spectrum at this point, but I don't think it makes sense to rush through things. We have only 5 more minutes. So if you have questions, please ask them.
I have a small conceptual question. Are there any situations where one wants to replace the category of abelian groups with the category of spectra?
Well, yes. One of them we already seen, actually, to find coefficients for general cohomology theories. Abelian groups are not enough. So that's one of them. Another one is sometimes you have objects that you would like to say that you can add them, but they don't add them strictly in a way. So you want to do a spectrum, and we're going to see an example in a couple of weeks, I think. But the idea is, for example, you can take vector spaces. You would like to say something like vector spaces form an abelian group. Well, okay, vector spaces form a commutative monoid under direct sum. But if you try to do that, you say that the associativity is true only up to isomorphism, for example. It's not true like literally on the nose. And if you take that, you get what's called an infinity space that we're going to define next time, I think. And if you take it, the associated group is actually going to be a spectrum. This is a monoid, so it's not quite a group. You need to add formal inverses. And what this spectrum is going to be the K-theory spectrum. So every time you want to add things, another example is, for example, when you take Bordism classes of manifolds. I'm going to be a bit vague about this. We're going to see, my plan is to show an example of this at the very end of this course, but you can take manifolds and Bordisms between them and again, you want to take disjoint union, and you would like to consider like the Bordism group of these things. Of course, you can take like Bordism classes, and that actually gives you a group. But that's taking the pi note of something, because you're collapsing things that are connected by a homotopy, by a Bordism, by an arrow. Or you can actually build a spectrum where these are actually the points. And I'm being a bit vague because there are choices you can make exactly what it means here. You can get stuff that's called MO. You can get also stuff that's called MTON or MTOD, and depending on exactly the details that you set up here. But these are circumstances, or I don't know. In general, spectra appear when you seem to have some relations you don't just want to collapse. And so you can take the abelian groups. Of course, for any spectrum, okay, I haven't defined it yet, and it's the very next thing I'm going to define. You can take its pi note, and that's going to be an abelian group. That's always allowed. But sometimes it's not the right thing. I mean, I won't say it's not the right thing to consider, but sometimes it pays to consider the spectrum. For example, in the case of algebraic K-theory, which is like K-theory for algebraic vector spaces, like without considering the topology in immersions, etc. If you want a statement like Galois descent for algebraic K-theory, okay, it's false for algebraic K-theory, but even to state it in a way that looks like it has some chance to be true, you need to state a level of spectra, not a level of abelian groups, which boils down in the existence of spectral sequences rather than just formulas. These is literally the fixed points of these. So you cannot really avoid this. I mean, again, from every spectrum you can build abelian groups, but you're forgetting structure, and this sometimes is problematic.
Cool. Does this then work for, you said, adding objects, and could this then work for every symmetric monoidal structure on a category 2?
Yes, indeed, it does. Next week we will start talking about these, as a matter of fact. It's what I consider actually the better motivation for spectra, but it takes a while to set it up. So unfortunately, we have to define spectra, prove they have limits, co-limits, and etc. today, and this stability property, which is very, very important. But yeah, I don't know if we're going to arrive to that definition next time. I hope so, but I don't want to be super fast. I have to still define the tensor product of spectra and a bunch of other stuff. But yeah.
Cool, thank you. I also have 2 questions regarding the last lecture.
Sure.
The first question was in the proof of the Brown representability theorem. We had this cool claim that made the proof work, and sometimes there were m greater than equal to 1, and sometimes there were m greater than equal to 0, and I got quite confused, and I don't know, do we need the greater than or equal to 0 for pointed spaces because we have pointed spaces, or does the m greater than or equal to 1
suffice? It should have been m greater or equal than 1, sorry. Okay. Sorry, that's a typo. Sorry about that. I'll fix it in the notes. Thank you for noticing it.
Okay, and so this is basically sufficient then because we have pointed spaces.
Connected pointed spaces. Very important.
Okay,
connected.
Yeah. Okay. Pointed. Yeah, okay, connected.
In fact, unfortunately, I decided that the counterexample was too complicated to give as an exercise. If I have time at some point, I might write it down as an appendix. But there is a counterexample if you don't have connected. and the problem is exactly that at some point I'm taking the kernel, and the kernel of pointed sets just don't work as well as kernels of groups. You cannot check that something is injective by proving it as trivial kernel in pointed sets.
Okay, cool. And the second question was from the last proof of the last lecture, this huge diagram where we put up the adjunction sigma infinity and omega infinity.
Yeah, this one?
Yeah, I did not quite understand the proof.
So, okay, I went perhaps too fast here, but okay.
No, the diagram part.
yeah, I was too fast on the diagram. So, okay, you understand these, of course.
Yeah.
And then these, that's basically by definition. And again, okay, I think you're okay until here, sort of. But then the question is, what are the transition maps? That's what I was sort of skipping over. Because this limit is exactly this diagram I wrote, but then you need to unwrap what it means to have the transition maps. And so, for example, oh, there is a plus n here, by the way, that was missing. So, for example, what can I say? Let me show, okay, the n equals m equals 0 is of course clear, I hope, part of the diagram. For n equals n is 0, and then the point is that, okay, this colimit in n is this vertical part of the diagram.
Yeah, but
this limit in n, but the question is, how do you map from n? And the point is that what is this map from colimit in m omega n sigma m plus nx to colimit omega m. Oh geez, this is so many m plus sorry, I have a map like this, and I have to turn it into a map like this, right? That's what this limit in n is doing. And we defined it by turning it by looping it. I have a map here downstairs, and I have to turn it into a map upstairs. That is what this limits n is doing. And I'm claiming that this is happening by looping. So, okay, and here, okay, this equivalence is clear, but here, so essentially you need, in the end, you have an equivalence like this. That's what this is claiming.
This is then
this is because omega commutes with filter colimits, actually.
Okay, is this then the last argument step?
This is just describing, if you want, these horizontal arrows. I'm just saying that these arrows don't go from here to here directly, but they pass through here.
Okay.
And you unwrap what these arrows are doing, and this arrow is just, including the m components to the m plus 1 components, which are in fact the same here.
Yeah, okay.
And then you unwrap what it means, and you get this big diagram here. And the limit of this big diagram is exactly the thing we want to conclude. But we know that this blue subpart of the diagram that I selected is given by equivalence. It's just a constant diagram. Just because the loop sigma, well, because E is a spectrum. And I'm claiming that I can take the limit of this big diagram by just taking on this sub diagram here, where it's just a constant diagram. And that's because every element in this big poset here is dominated by some element in this subdiagram here. There is some element here that's bigger, that dominates it.
I don't see where you're pointing.
Oh, sorry, I'm trying to. So every element in this diagram here, let's say this one, there is some element in this subdiagram here. Ooh, and this arrow goes this way actually. Here, for example, that is bigger.
Ah, okay.
And everything is co-filtered actually. It's the opposite of filtered, but okay. That's because we're a limit and not co-limits.
This is like a co-finality.
That's that's co-initiality actually argument.
Co-initiality, okay.
Yeah. Because we're limit and not co-limits, but okay, that's just terminology. The idea is the same.
Yeah.
And so you can take.
Yeah. Because in the script you wrote that one would first take the vertical limits and then the horizontal limits, but I didn't quite get this.
Yeah, but that's actually what this formula is saying. This is the limit over n, which is the limit over here of the limit over m. That's saying if you take first the vertical and then the horizontal limit, you can get this limit that we want to compute. But then you can also take first, if you want, the diagonal limit. That's a constant one. Sorry, first the horizontal limit and then the diagonal limit, so to say. I don't know. If you take first the horizontal limit, then you end up, oh, actually, that's a better way of saying it, perhaps. If you take first the horizontal limit, you end up with this diagram here, exactly, because you're taking the top, the beginning of every row, because every row is finite.
Ah, okay, so because every row is finite.
Has a biggest object. When you take a limit of a diagram with a biggest object, that's just what it is.
Oh yeah, you're right, yeah.
And then what you're left with is exactly this diagonal argument, this diagonal guy here, which is constant. Okay. Yeah, I probably should have written it, instead of saying the leftmost diagonal map is cofinal, which is also should be co-initial and whatever, I should probably have written it in that other way, taking first the limits in the rows and then in the columns.
Yeah. Okay, cool. Thank you.
Okay, let me stop the recording.